In this video, we'll look at one last example of a hypothesis test for a single mean. This time we'll be using the raw data rather than the summary statistics. So according to the U.S. Census Bureau, the mean family size in the U.S. is 3.13. So they're telling me that the population mean is equal to 3.13. A sample of the college math class resulted in the following family sizes. So we've got all of these right here listed out. We haven't actually gone and calculated the mean or the standard deviation. We just have this raw data. Using a significance level of alpha equals 0.01, test the claim that the class's mean family size is greater than the national average. You may assume that the necessary conditions are met. So this on the face looks pretty similar to the hypothesis testing problem that we looked at in the last video. The one major difference is we're not provided with a sample mean. We don't know what X bar is, and we don't know what our sample standard deviation is. We have to go find those ourselves. So to start off, this problem is going to look pretty similar to the last one. We're going to say, okay, well, we should list what's our null hypothesis, what's our alternative hypothesis. In other words, what is H naught? What is HA? So here we're testing the claim that the class's mean family size. So we're looking at a population mean. So we're going to be looking at population mean mu for both of these two statements. And the claim here is that the class's mean family size is greater than the national average. So we're saying greater than for our claim, which is our alternative hypothesis, greater than the national average, which we set up here was 3.13. So it's greater than 3.13. Once we have our alternative hypothesis, the null hypothesis is always a statement of equality. Its mu is equal to 3.13. So we've got our null hypothesis and our alternative hypothesis. Normally at this point you would go and list out some of your other summary statistics, but we don't have those right now. We don't have X bar and we don't have S. However, we do have the raw data, which has been provided to us right here. That is something that we can go ahead and calculate. So we're going to use our graphing calculator to just do some of the heavy lifting here for us, make sure we don't make a silly mistake, something like that. So I'm going to hop over to my graphing calculator just to remind us of what that process is going to look like. Oops, sorry about the ad. So first thing that we need to do is we need to enter this data into our graphing calculator. And to do that, I'm going to press stats, and then I'm going to choose that very first option, number 1, edit. Now, I've gone ahead and entered all of the data in already. If you need to pause the video on your own, if you're following along with this problem and you want to enter that data in, go ahead and give it a quick pause, enter this in. We should end up with 24 data values in our data set. So once we have that, we can go ahead and calculate the sample mean and the sample standard deviation. So to do that, I'm going to press stat. I'm going to arrow over to the right one time so that I'm under calc and it says 1 var stats. We're just going to go ahead and press enter, and then we can go down to calculate, and that's the one we're going to choose. And we have our sample mean is 3.83, and our sample standard deviation, remember that's S, is 1.43. The other thing that's worth mentioning here is our sample size. You could count up the number of data values that you have, but the calculator lists that right below. It says N is equal to 24, so that's going to be a helpful piece of information. So let's go ahead and make notes of what all of those different values are. We said our sample mean was 3.83. Our sample standard deviation S was 1.43. And our sample size N was 24. And then, of course, we'll just make a quick note as well. Our alpha is 0.01. So those are all of our summary statistics. That's extremely helpful to have when it comes to listing out or calculating the standard error and the test statistic and so on and so forth. So there's my first step. Second thing that I want to do is check my conditions. Remember, my conditions are independent sampling, which we use random sampling as a proxy, and then a large enough sample size, meaning n is greater than or equal to 30, or if we don't have a large enough sample size, the underlying population is normally distributed. In this case, we can cheat a little bit. It says you may assume that the necessary conditions are met. So it's just telling us, hey, you can assume that the conditions are met. We don't have to worry about that part. Because we would have to worry about that part because our sample size isn't quite big enough. So we would have to hope that our underlying population is normal. In any case, we can move on to the third step, which is where we're going to do our calculations. So step 3 is where we're going to calculate our standard error, our test statistic, and estimate our p-value. So I would encourage you at this point to pause the video and try these calculations out on your own if you have not done so already. But I'm going to go ahead and continue working, assuming that you've already done that, you've paused it, you've tried these out. My standard error, remember that formula looks like S divided by square root of n. So S being my sample standard deviation, 1.43, divided by the square root of my sample size is 24. So grabbing my calculator real quick, 1.43 divided by the square root of 24, I ended up with 0.292 if I round to 3 decimal places. So there's my standard error. Next thing I need to calculate is my test statistic. So my test stat, remember we're using our t distribution. So it's t is equal to our sample mean, x bar, minus mu naught, divided by our standard error. So x bar coming from the sample mean, we calculated that out earlier as 3.83. So 3.83 minus mu naught, remember that's the number that's coming from our null and alternative hypothesis, which in this problem is 3.13. So minus 3.13 divided by the standard error that we just calculated out to be 0.292. So I have 3.83 minus 3.13 divided by 0.292, and this time around I end up with 2.397 for my test statistic. So there is t. So there's the first part of my calculation that I need, my test statistic. I'm going to use that next to help me find my p-value. But before I can do that, I need to know two things. I need to know my degrees of freedom, which remember is n minus 1. So in this case, my degrees of freedom are 24 minus 1 gives me 23. So I have 23 degrees of freedom. The other thing that I want to make sure that I mention is what type of test we're doing. Are we doing a one-tailed test or a two-tailed test? And for that, remember, we're looking back at our alternative hypothesis. In this case, it says mu is greater than 3.13, which means we're doing a right-tailed test. So this is going to be a one-tailed test because we're only talking about the area to the right. We're only talking about the area on one side of my distribution. Only if it says not equal to, that is when we would use a two-tailed test. If it's less than or greater than, that falls under the category of a one-tailed test. So we have everything we need at this point. Let me make a quick note here. My degrees of freedom are 23. We're ready to go and calculate our p-value. So hopping over to my t-table once more, let's just go ahead and erase and start fresh. Make sure we don't get confused by anything that I wrote earlier. Okay, so we said our degrees of freedom are 23, and our test statistic was t is equal to 2.397. So degrees of freedom are 23. That means we're looking at this row right here. We should be able to zoom in just a little bit. So we're looking at that row that I've highlighted. And then I'm going to look for where does 2.397 live? Where does that live in my list of numbers? And in this case, it's going to live somewhere between 2.07 and 2.50. So I'm looking at this range. We also said, one other thing I want to mention, is that we were doing a one-tailed test because our alternative hypothesis said mu is greater than, I believe it was 3.13. So that means we're doing a one-tailed test. We're looking at these probabilities up here. So that means that my p-value is going to be somewhere between 0.01 and 0.25. So it's somewhere in that range. Remember, I can't say exactly what it is using this method. I can just have an idea of where it lives, and that's enough information for me to make my decision and answer my question. So hopping back, we said our p-value is between 0.01 and 0.025, which should be enough information to help me make my decision at the end of this problem. So we've got our calculations, we've got our p-value, we've got our test statistic. That's what we needed in that third step. Now in step 4, we can go ahead and make our decision and then talk about what that decision means within the context of our problem. So our alpha, we said was, let me scroll back up here, we said alpha was 0.01. So alpha was 0.01. I'm comparing the alpha to this p-value that I found at the end of step 3. And what I found was the p-values between 0.01 and 0.025. So when I asked the question, is the p-value less than alpha? Well, if it's between these two, that means it's going to be bigger than 0.01. So the answer to that question is no, the p-value is not less than alpha. If you wanted to write this out, we would say that the p-value is greater than alpha. So if the p-value is greater than alpha, using the same decision-making rule that we've always looked at, that means that we do not reject H0. Do not reject H0, which means that we do not change our mind. Remember, that means that there is not enough evidence to support the alternative hypothesis. So if I'm going to talk about what this decision means within the context of my problem, there is not enough evidence to support that, and I'm going to go back up here and support that the class's mean family size is greater than the national average. That the class's mean family size is greater than the national average. You could even say greater than 3.13 if you want to save yourself a little bit of writing here. So once we have those summary statistics of X bar and S and N, the rest of this problem should look exactly the same as we saw in the last video where, we calculate our standard error, our test statistic, our p-value, and the decision-making process is all exactly the same as we saw before.